I think it will be helpful to you to see a number of examples of triangle congruence proofs. So let's do that in this section. I think I have 5 for you. And I have a suggestion about how you should watch this. Once I've talked about the setup of the proof, I think it would be helpful to you if you were to pause the video and attempt to give the proof yourself. And then once you've made an attempt and hopefully successfully made an attempt, you can look back and compare what you did to what I did. Now, there'll be no reason to assume that even if we have both done the proof correctly, that we will have given the same proof, as I have pointed out a number of times. In many cases, multiple different proofs are possible for a single result. But still, I think it would be helpful for you to do that. So let's have some examples of this. Oh, and another point that I should make before we launch into this. This, in a way, I think is really an example of what the chapter is all about. Yes, we have a number of triangle congruence principles from this chapter, side angle side and side 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 and angle side angle. And later on, we'll have angle angle side and also something called hypotenuse leg. We'll talk about that later on. And yes, we did some work to prove these, quite a bit of work actually. But really, the point of the chapter is just the development of these tools and then the use of these tools. So what we really do in this chapter and all throughout the year is we build certain tools and then we use those tools. So let me show you some good examples of how the tool set that we developed in this chapter can be put to use. So let's take a look at our first proof. And as always, I would suggest that you take a little bit of time just to digest what's been said to you, to look at the diagram, read the given, read what you're supposed to prove, label the diagram with the given. I would suggest that you not label it with what you're supposed to prove, because that would likely become a temptation to assume that the conclusion is true at the start. But of course, you're never supposed to do that. So let's digest. So I see a diagram with multiple triangles, and I am told that AB is equal to BC. So I will definitely mark that into the diagram, because we are told that that is the case. Then I'm told that D and E are the midpoints respectively of AE and CD. So D is the midpoint of AE. So the 2 points of AE are equal. Oops, better use 2 hash marks. And then E is the midpoint of CD. Which means that the 2 parts of CD are equal. Oh, and a conclusion here becomes rather obvious, doesn't it? That all the parts, all 3 parts of AC must be equal to one another. That's something I expect will be said in the proof. And then we're supposed to prove that BD is equal to DE. Okay, so before you pause and attempt to give this proof yourself, do keep this in mind. What we're asked to prove here is that a pair of segments are equal to one another, and typically the way that that gets done, not always, but typically, as I have noted before, is to prove that triangles are congruent and then use CPCTE. So you might wish to consider that strategy. So again, my suggestion is this: pause the video and attempt to give the proof. And then once you've given it an attempt, hopefully successfully, you can come back and listen. All right, welcome back. Let's give this proof. So we wish to prove that BD is equal to BE. So how could this be done? Well, what I notice is that BD is part of triangle ABD and BE is part of triangle CBE. So let me attempt to prove that triangle ABD is congruent to triangle CBE. Well, I'm close to that with what I noted in the diagram with the hash marks, because I knew that 2 sides of one of those is equal to 2 sides of the other. So if I could get another equation, hopefully a pair of included equal angles equal, then I could use side angle side congruence to prove the triangle's congruent, and then conclude that BD is equal to BE by CPCTE. So the real point here, the real goal, I suppose, is to prove that triangle BAD is congruent to triangle BCE. Not triangle, but angle, that angle BAD is equal to angle BCE. Then how can we do that? Well, shift your point of view, as it were. I asked you a moment ago to consider triangles ABD and CBE. Now consider a different triangle, triangle ABC, the largest of the triangles present in the diagram. That is a particular kind of triangle. In that triangle, AB is equal to BC. So that triangle is isosceles. That means that we can apply the isosceles triangle theorem to that triangle to get that angle A is equal to angle C. Oh, and then that's precisely what we needed to go and prove a pair of triangles congruent. So we could reach our conclusion. Okay, so statement and from and by. And I think that for some of the proofs in this section, I'll begin to give so-called paragraph proofs, where we simply write the proofs out line by line, paragraph by paragraph. But here at the start, I'll do a column style proof. So the given, of course. And then let's see. What did we note first of all? We noted that AD has to equal DE. And we noted as well that DE has to equal EC. And that comes from the given, of course, by the definition of midpoint. And then, as we noted, this of course implies that AD, let me make that look like a C. This implies that AD is equal to EC, and that follows from 2 by the transitivity of equality. And then, as I noted, we can apply the isosceles triangle theorem to triangle ABC. So we can say that the measure of angle A is equal to the measure of angle C, and that follows from the given, where we're told that we have a pair of equal sides, by the isosceles triangle theorem. So I'll go ahead and put that into the diagram because we've actually proven that that is the case. And now it follows that triangle ABD is congruent to triangle CBE by SAS congruence. That's the SAS pattern. Two sides equal to two sides. The included angles equal, so SAS. And let's see, where is the information to use SAS? Well, part of it's in line number 1. That is the AB equals BC. That was in the given. We also needed the AD equal EC, which is in line number 3. And we also needed the pair of included equal angles, which is in line number 4. And then once we have that ABD is congruent to CBE, then we can conclude by CPCTE that BD is equal to BE. Okay, so that comes to us from 5 by CPCTE. And with that, the proof is complete. So there we go. That's our first proof. All right, on to the second. All right, so again, let's digest. And after we digest, you can pause and try to do the proof yourself. So we're given that in this diagram, the measure of angle ABE, let's mark this, is equal to the measure of angle ACD. And again, I highly suggest that you mark the information that's present in the given. And we're told as well that AB is equal to CE. Now, this is a bit hard to label because AB is broken up into two parts, and AC is broken up into two parts as well. So if we were just to put a hash mark on that, we wouldn't be able to see. Sorry, I need to make that go away. So I will make that go away. If I can make that go away, I don't want to have to start over. So yeah, there we go. I made it go away. Sorry about the interruption. So we know that AB is equal to AC, but AB and AC are broken up into two parts. So if we put a hash mark in there anywhere, it would be difficult to know what it applied to. So sometimes I will do this. I will put that mark in to indicate that we have all of AB, and a second to indicate that we have all of AC, and I'll put the hash mark on that. I find that that's a clear way to label a diagram, though, do what you think is clear. And we wish to prove that BD is equal to CE. Okay, so BD is equal to CE. So maybe triangle congruence? Or let me make another suggestion to you before you pause and attempt to do this proof yourself. One way that occasionally we prove that a segment is equal to a segment is by subtraction. That is, consider in this case what would follow if we were able to say that AD, again, AD is equal to AE. Well, then we could subtract AD from AB, AE from AC, and we would then get that BD is equal to CE, because of course equals taken from equals are equal. So there was a theorem back in chapter 3 that said something like this. That is, if you have equal wholes and all parts except for one pair equal, then the parts that remain must be equal as well. I'll tend to call this just simply equals taken from equals are equals. Okay, so there's a suggestion about how it is that you might approach this. So pause and try it. All right, so let's do it ourselves. And I tell you what, I'll give our first paragraph proof. So let's see. We wish to prove that BD is equal to CE. Okay, and we could do that, as I said a moment ago, if we got AD equal to AE. So let me say this. And this ultimately is an example of why it is that paragraph proof is more versatile and I think superior to column proof, though there's nothing logically wrong with column proof. What I mean is this, is that in a paragraph style proof, you can interject material that isn't logically required but does help to make the proof clear for the reader. Um, so let me do that. Let me make a note to the reader about what it is that I intend to prove. Let us prove that AD is equal to AE. Okay, so I just sort of focus the reader's mind to tell them what it is that we intend to do. So let us prove that AD is equal to AE. Well, how will we do that? Well, consider two triangles, triangle ABE and ACD. We can prove those triangles congruent. Indeed, we have almost all the information to do so. And then once we get them congruent, we will have that AD is equal to AE, and we will be able to finish the proof. So uh, let me make another little note to the reader. To do this, we'll prove that triangle ABE is congruent to triangle ACD. And this is certainly one of those proofs where it's a matter of focus, right? I mean, there's some complexity in the diagram, and it can be difficult to pick out the triangles that are like important to the particular moment. And the ones that I wish you to focus on at this moment are ABE and ACD. Okay, so those are the ones that we will prove congruent to one another. So, well, we already know from the given, of course, that the measure of angle ABE is equal to the measure of angle ACD, and likewise that AB is equal to AC, B is equal to AC. So that's two equations of the three that we need to prove those two triangles congruent. And then note this as well, and perhaps you've note as well that angle A is part of both. Oops. And the way that we've noted this in our column style proofs is to say that AB is equal to AB. So this is logically equivalent to that. But I'll say it just like this, okay? And maybe pause here for a moment to note that, I mean, logically this would be the same as a column proof, but I think perhaps it would be easier to follow than the column style proof, because the column style proof you would just launch into this triangle congruence proof to prove that ABE is congruent to ACD, and the reader might think, what are we up to here? Why do we have to do that? They might not even realize that you're headed to a triangle congruence proof. So this I think is a bit easier to read. Now ultimately I'll accept either kind of proof. I mean, you make your choice. But we will ease our way into paragraph proof. Oh, and another point that I wish to make here. Paragraph proof is a creative kind of process for sure, in a way that column style proof is, because you have this freedom to, like, attempt to explain to the reader in the best possible way how this proof proceeds. And I know that if I were to write this proof out again, I would do it at least in a slightly different fashion, okay? And no doubt if you were to write this proof out yourself after you've seen it, if you were to attempt to recreate the logic of it in paragraph form, you would do it somewhat differently than I have done it. That's just the nature of paragraph style proof. So now here we can say, that triangle ABE, ABE, triangle ABE is congruent to triangle ACD by SA. Ooh, got to be careful about this. Ooh, I also have to get rid of the junk. It's not SAS, is it? It's angle side angle, because as we noted, A is a part of both, right? So that's angle side angle congruence by ASA congruence. And do note that even though this is paragraph style, the logical standard is still the same. We make statements, and we give reasons for them, right? Okay, so that's what it takes ultimately to create a proof, and we have done that. And thus, by CPCTE, it follows that AD is equal to AE. And we can go ahead and finish this up. And since equals taken from equals are of course equal, and of course what I have in mind here is this. It's weird. And since equals taken from equals are equal, of course, and what I mean here is we have the equals AD and AE taken from the equals AB and BC, it will then follow that what remains is equal as well. So BD is equal to CE. So there we go. So there's our first paragraph style proof. All right, so here we go to the next. All right, so perhaps I'll try to accelerate a little bit. So I'm told in this case that the measure of angle CAB, let me mark this, is equal to the measure of angle CBA. And I'm told as well that the measure of angle DAB, ooh, that whole thing, right? So let me try to indicate the whole thing like that, is equal to the measure of angle DBA. Ooh, interesting. So those are equal, and we wish to prove that DC bisects angle ADB. Okay, DC bisects angle ADB. Now, before you try this yourself, do note this, that the way that you would show, surely, that DC bisects angle ADB is you would prove that, I'll give names to them, you would prove that angles 1 and 2 are equal. And once you know that angles 1 and 2 are equal, it would follow, by definition of bisects, that DC bisects angle ADB. So that's really the goal, to prove that those two angles are equal. Oh, and it's perfectly fine to put labels in for angles in any diagram that you care to do. All right, so attempt this yourself. All right, so let's see what we can do. Well, how are we going to get this done? How are we going to get that angle 1 equal to that angle 2? Well, a really good guess here, of course, is CPCTE. And how will we be able to use CPCTE? Well, of course, we'll have to have triangles congruent to one another. And how are we going to get triangles congruent to one another? Well, there is a result, okay? And I will remind you of this. Hopefully you haven't forgotten it yet. A result that I had you prove on one of the worksheets. That result is called the converse of the isosceles triangle theorem. The isosceles triangle theorem itself says that in a triangle with equal sides, the angles opposite those equal sides are themselves equal. The converse of the ITT says that in a triangle with a pair of equal angles, the sides opposite those equal angles are themselves equal. So here's what has to follow. By converse ITT, that'll have to follow that AC is equal to CB, and it will also have to follow that AD is equal to DB. Because in triangle ACB, we have a pair of equal angles, and in triangle ADB, we have a pair of equal angles. So we'll get, again, AC equals CB. We'll get AD equals DB, but of course DC is equal to DC, so it then will follow that triangle ACD is congruent to triangle BCD by side, side, side. And then it will follow by CPCTE that angle 1 is equal to angle 2. Okay, so let me write this out. By con ITT, that is the converse of the isosceles triangle theorem, it will follow that AC is equal to BC, and it will follow that AD is equal to DB. And moreover, DC equals DC. And I tell you what, I mean, that's so obviously true that I won't even mention the rule here. Of course, it is reflexivity, but nobody will doubt that DC is equal to DC. And thus, that's a really good word for proofs, isn't it? Thus, it indicates that we've drawn this new statement out of what became before. So thus, by SSS congruence, it follows that triangle ADC is congruent to triangle, and I'm going to be really careful about the order of the letters. If I said ADC for the first, it would have to be BDC, DC. Tell you what, I'm going to clean that up a little bit. BDC for the second. And then we get to finish the proof up. And then by CPCTE, it follows that the measure of angle 1, C, I'm going to use the label that I created, equals the measure of angle 2, meaning that DC bisects angle ADB by, of course, the definition of bisects. And with that, the proof is complete. Okay, so that's our next proof. We've got 2 more to do, and they get a little bit harder. Okay, so here's the next. We're told that triangle AFC, take a look at triangle AFC, is congruent to triangle EGC. Oh, and that is so much information. Remember that congruence means that all sides that correspond are equal, all angles that correspond are equal, and that for triangles is 6 equations. So that part of the given right there, the congruent statement, is really shorthand for 6 total equations. That is so much information. We'll have to think about what part of that we will need, and we'll definitely need at least one of those equations, maybe more than one. All right, we're told as well that F bisects AB. Okay. And we're told that G bisects DE. Okay, so that is that AB is broken up into 2 equal parts and DE is broken up into 2 equal parts. And then we're supposed to prove that BFC is congruent to DGC. That BFC is congruent to DGC. And of course, you would do that with, well, what are the possibilities here? Side angle side, or side side side, or angle side angle. Okay. All right, give this a try. All right, so here we go. Let's do this proof together. I don't know, it doesn't particularly matter, I suppose, but I'll do this as a 3-column proof. Do it as paragraph if you like. I mean, ultimately, it's up to you how it is that you give your proofs, just so long as they're logically correct, of course. So let's see. AFC is congruent to EGC. That means that everything in them, all the parts that correspond, are equal. So let's perhaps come back and think about how it is that we'll actually use that. So we're told that F bisects AB. So AB is broken up into 2 equal parts. G bisects DE. So it's broken up into 2 equal parts. Oh, but AFC was congruent to EGC, which meant that AF, of course, was equal to GE by CPCTE. But then BF is equal to AF and DG is equal to GE because, of course, we have bisectors. Bisects always means cut into 2 equal parts. So all 4 of those pieces, AF and FB and DG and GE, must be equal to one another. That's something we'll easily be able to infer. And then let's see. We wish to prove that BFC is congruent to DGC. Well, so far so good, right? I mean, we do have BF equal to DG. BF equal to DG, so that's one pair of sides equal. Is there anything else that we know could be equal in these 2 triangles? Oh, wow. Have you noticed this? Why is what I just drew into the diagram true? VAT, of course, that's the vertical angles theorem. Remember that the one universal assumption that we're able to make, unless I tell you not to, is that what looks straight is straight. So we have vertical angles there. So they are equal to one another. So, we're like 2/3 of the way to the congruence of triangles BFC and DGC. So what else could we use? Interesting. I'm trying to get something else here. Oh, well, look, we also know that FC is equal to CG, right? Because that follows from the given congruence that AFC is congruent to EGC. And then somebody might go, oh, well, we now know that triangle BFC is congruent to triangle DGC, and that's side angle side. And at that point, I would say it is not side angle side. The angles that would have to be equal are, I'm going to put dots on them momentarily. The angles that would have to be equal are BFC and DGC. Those are the included angles, but those are not the ones that we are told are equal. What is the actual pattern here? Let me erase those dots. Of the given equations, given inequalities, it's ASS, isn't it? The naughty one, and that one doesn't work. So let's think about what else we could prove to be true. Well, let's see. Maybe the vertical angles is not actually going to help us. Sometimes you realize something is true and it doesn't actually help you in the end. So let's think, for instance, about angles 1 and 2. Those are angles of triangles AFC and EGC. As a matter of fact, they're angles that correspond in those two. So they have to be equal to one another, right? Okay, so yeah, of course, by CPCTE, they have to be equal to one another. And now look at angles 3 and 4. Oh, what's angle 1's relationship to angle 3? Linear pair, of course, which means they're supplementary. Same for 2 and 4. Oh, and then what does that mean? That angles 3 and 4 are supplementary to equal angles. And what do you know about angles supplementary to equal angles? They are themselves equal. So it'll follow that angle 3 is equal to angle 4, oh, which is the pair of angles that we needed equal to apply sine angle side congruence. Okay, so I think I've seen a way for the proof, so let's actually give the proof. So let's see, what did we know to be the case? We knew that AF was equal to GE, and that followed from the given by CPCTE. And we also knew that AF is equal to FB, and we knew that DG is equal to GE. That also followed from the given by the definition of bisects. We could, of course, use midpoint terminology if we wanted, but bisects means the same, cuts into two equal parts. And then think about what all of these mean, right? If you put all of these together, it will follow that FB is equal to DG. And that follows from 2 and 3 by the transitivity of equality. Things equal to equal things are themselves equal. That's just what transitivity tells us. So that's the transitivity of equality. And what else did we need to say? Oh, we also wanted to say that FC was equal to GC, and that follows from the congruence that we were given. Okay, so that's CPCTE. Oh, and remember we said as well that the measure of angle 1 is equal to the measure of angle 2. That also followed by CPCTE. Remember I told you at the start that congruence that we were given, triangle AFC congruent to triangle EGC, that is so much information. That's 6 total equations. Well, you know, we've used 3 of those. So it's not a surprise that that has been used repeatedly. Okay, it's been used repeatedly. So that was the measure of 1 equal to the measure of angle 2. But of course, here's what follows by the linear pairs theorem. So angles 1 and 3 supplementary, and likewise angles 2 and 4 are supplementary, and that follows from ultimately the given again, because the given is just that, you know, what straight is straight tells us that we have linear pairs, and that follows by the linear pairs theorem. And then let's see, we now have 2 angles, namely 3 and 4, supplementary to equal angles. So it follows that the measure of 3 is equal to, oops, that's a mess. It follows that the measure of 3 is equal to the measure of 4. From 7, and that's the same supplements theorem. Angles supplementary to equal angles are themselves equal. And then with that, we have everything we need to declare that triangles are congruent. We have 2 sides of one congruent to 2 sides of the other, equal to 2 sides of the other. We have the included angles equal as well. So it now follows that triangle BFC is congruent to triangle DGC. And that follows by SAS congruence. And let's go and find all the places where we have equations that we need for that. Well, we need line number 8, that's the angle equal to an angle. We needed FC equal to GC. Okay, so that's line number 5. And we also needed that FB is equal to DG. So that's line number 4. Okay, so there we go. The proof is complete. All right.